Josiah Willard Gibbs on the Equilibrium of Heterogeneous Substances, published between 1875 and 1878, represents a profound synthesis of thermodynamics. This synthesis enabled the prediction of equilibrium states in complex multiphase systems. Gibbs' treatise, initially met with some bewilderment, ultimately reshaped both theoretical and industrial chemistry. This work addressed a fundamental challenge facing chemists and engineers predicting the behavior of systems containing multiple phases and components, such as mixtures of gases, solutions, and alloys. Prior to Gibbs, understanding such systems relied heavily upon empirical observations and lacked a rigorous theoretical framework. Gibbs provided this framework. His approach centered on applying the principles of thermodynamics, particularly entropy, energy, and chemical potential, to derive conditions for equilibrium. Notably, he formulated the celebrated Gibbs Phase Rule, a deceptively simple equation that governs the number of degrees of freedom in a heterogeneous system. The Gibbs Phase Rule stands as a cornerstone of physical chemistry. It relates the number of phases, components, and degrees of freedom in a system at equilibrium through the concise equation F equals C minus P plus 2, where F represents the number of degrees of freedom, C represents the number of components, and P represents the number of phases. Degrees of freedom are intensive variables that can be independently changed without altering the number of phases. Components refer to the minimum number of independent chemical constituents necessary to specify the composition of all phases in the system. Phases are homogeneous regions of the system separated by distinct interfaces. For example, water has 3 phases: ice, liquid water, and steam. The components for a simple solution of salt and water would be salt and water, for water, satisfying the equation. In a system with one component, water, and one phase, steam, the degrees of freedom equals 1 minus 1 plus 2, therefore 2. Both temperature and pressure can be altered independently. Gibbs derived this rule through rigorous mathematical analysis, employing partial derivatives and thermodynamic potentials to characterize the equilibrium state. His analysis hinged on the minimization of the Gibbs Free Energy, defined as J equals H minus Ts, where H is enthalpy, T is absolute temperature, and S is entropy. At constant temperature and pressure, a system reaches equilibrium while its Gibbs free energy is minimized. This principle allowed Gibbs to express equilibrium conditions in terms of chemical potentials, denoted by mu sub I, which represent the change in Gibbs free energy with respect to a change in the number of moles of component I, holding temperature, pressure, and the number of moles of other components constant. The chemical potential of a substance represents the change in the system's Gibbs free energy when 1 mole of the substance is added, while temperature and pressure remain the same. Mathematically, this is expressed as the partial derivative of G with respect to N sub I, subject to constant temperature, and constant N sub J, where I does equal J. In simpler terms, it measures the escaping tendency of a component from a phase and dictates the equilibrium distribution of components among different phases. The significance of Gibbs' work extended beyond mere theoretical elegance. It offered a powerful tool for understanding and optimizing industrial processes. Consider, for example, the metallurgy industry of the late 19th century. The production of steel involved complex mixtures of iron, carbon, and other elements existing in various phases. Gibbs' framework provided a means to predict the conditions necessary to achieve desired compositions and microstructures, leading to improved material properties. Likewise, in the emerging field of steam power, his analysis of phase transitions, such as the boiling of water, provided a theoretical basis for optimizing the efficiency of steam engines. Gibbs' contributions did not occur in a vacuum. He built upon the foundations laid by his predecessors, most notably Rudolf Clausius and James Clerk Maxwell. Clausius' concept of entropy, a measure of disorder in a system, played a central role in Gibbs' formulation of equilibrium criteria. Gibbs adopted the formula for entropy of an ideal gas from Clausius. Maxwell's statistical mechanics, which sought to link microscopic properties of matter to macroscopic thermodynamic behavior, provided a deeper understanding of the underlying principles governing equilibrium. Gibbs was particularly influenced by Maxwell's work on the distribution of molecular velocities in a gas, and extended this approach to analyze the statistical behavior of ensembles of identical systems. Gibbs' insights into the behavior of real gases led him to develop a statistical mechanical formulation of thermodynamics, providing a molecular interpretation of entropy and chemical potential. For instance, Gibbs introduced the concept of the Gibbs paradox when considering the entropy of mixing of ideal gases. When 2 identical gases are mixed, there is no change in entropy. However, when different gases are mixed, there is an increase in entropy proportional to the number of particles and the logarithm of the volume ratio. This thought experiment highlighted the importance of the indistinguishability of particles in statistical mechanics. Gibbs found the paradox resolved itself when properly accounting for particle indistinguishability. This laid the groundwork for later developments in quantum statistics. For example, a system composed of two identical compartments with n particles in each would have its entropy precisely doubled compared to a single compartment with n particles. Gibbs' work further provided a theoretical foundation for understanding specific chemical reactions and phase transitions. One illuminating example is the Haber-Bosch process that synthesizes ammonia from nitrogen and hydrogen. In this process, nitrogen gas and hydrogen gas combine at high temperatures and high pressures. This results in the production of ammonia gas. Gibbs Free Energy calculations, guided by Gibbs principles, allow engineers to optimize reaction conditions, maximizing ammonia yield while minimizing energy consumption. His formulation provided the quantitative tools for designing efficient chemical reactors, profoundly impacting the chemical industry. The impact of Gibbs on the equilibrium of heterogeneous substances extended far beyond theoretical musings, finding validation through meticulous experimentation. Early experimental verifications of the Gibbs Phase Rule, which dictates the degrees of freedom in a heterogeneous system, came from studies of salt hydrates and alloys. For instance, the behavior of water, ice, and water vapor at varying temperatures and pressures precisely aligned with the phase rule's predictions, solidifying its credibility. Similarly, the solidification processes of binary metal alloys, such as lead-tin systems, exhibited phase diagrams entirely consistent with Gibbs' equilibrium conditions. Despite its predictive power, Gibbs' work initially faced skepticism. Many chemists, accustomed to empirical observations and hands-on experimentation, found his mathematically dense treatment off-putting and lacking immediate practical relevance. A prominent champion emerged in Hendrik Willem Bakhuis Roozeboom, a Dutch chemist. He meticulously conducted experimental studies of phase equilibria in various chemical systems. His work demonstrated the phase rule's utility in understanding the complex behavior of salt solutions and alloys. Roozeboom's carefully constructed phase diagrams visually elucidated Gibbs' abstract concepts, making them accessible to a wider audience and galvanizing acceptance within the scientific community. Gibbs' thermodynamics profoundly shaped the development of physical chemistry, influencing luminaries such as Wilhelm Ostwald, Jacobus Henricus van 't Hoff, and Santo Henius. Ostwald rigorously promoted Gibbs' ideas, integrating them into his systematic approach to chemical phenomena. Van 't Hoff, known for his groundbreaking work on chemical kinetics and osmotic pressure, directly applied Gibbs' concept of chemical potential to understand the behavior of solutions. For example, the chemical potential difference between a dilute solution and a pure solvent drives the phenomenon of osmosis, allowing for the precise calculation of osmotic pressure based on solution concentration and temperature. Arrhenius, who formulated the theory of electrolytic dissociation, drew upon Gibbsian thermodynamics to explain the thermodynamic properties of ions in solution. The enduring relevance of Gibbs' work extends into modern science and engineering. Chemical engineers routinely employ Gibbs free energy calculations to optimize chemical processes, ensuring efficient and economical production of various chemicals and materials. In materials science, Gibbsian thermodynamics offers insights into phase transformations, alloy design, and the stability of ceramic materials at high temperatures. For instance, the design of high-temperature superconductors hinges on understanding the stability of complex oxide phases, which are governed by Gibbs free energy minimization principles. Nanotechnology draws heavily upon Gibbs' surface thermodynamics to understand the behavior of nanoparticles and interfaces. The stability and self-assembly of nanoparticles are critically dependent on the interfacial energies governed by Gibbs equations. Understanding how surface tension, particle size, and surrounding environment affect nanoparticle behavior is very important for designing effective drug delivery systems, catalysts, and electrolytic devices. The Kelvin equation, derived from Gibbs' work, predicts the vapor pressure of small droplets or particles, providing a crucial tool for manipulating and controlling the properties of nanomaterials. In conclusion, Josiah Willard Gibbs on the Equilibrium of Heterogeneous Substances represents a towering achievement in the history of science. Its rigorous mathematical framework revolutionized thermodynamics, providing a unified approach to understanding equilibrium in diverse physical and chemical systems. While initially met with skepticism, his ideas were validated through experimental studies. The work served as a cornerstone for the development of physical chemistry, chemical engineering, material science, and nanotechnology. Gibbs' legacy lies in his ability to transcend empirical observations. He offered a deep abstract, mathematical perspective on the physical world, his contribution had a permanent effect on how scientists approach complex systems. His impact is enduring. His work continues to inform and inspire scientific innovation. His emphasis on mathematical rigor moved science from descriptions to predictions. This reflects a paradigm shift that continues to shape scientific inquiry.